Okay, let's continue on with some more examples of two-dimensional vectors. This is really done in more detail in grade 12. It is part of the grade 11 curriculum, but I know it's not gone into much detail by most teachers, but I feel it's important that I introduce you to them because most of you have indicated you're taking grade 12 later. So at most I would give you a single problem on Friday's test on this. Here's a classic one in a crosswind or a cross current. So let's suppose you're in a plane and you're flying at 3 kilometers an hour east, a very slow plane. And there's a wind that's coming in towards the north. And the wind is blowing 4 kilometers an hour north. What's the plane's actual vector going to be? And the plane will actually be blown on this course. So how do we calculate the plane's vector? We just add up the velocity of the plane and the velocity of the wind. And that's the way you would write it in vector notation, but to actually solve it for the size of that vector and its direction, you'd use a little bit of trig. So this total is called a resultant. We calculate this vector just using good old pythagorassess theory. Pop your numbers in and you get your answer. Would I require you to write all these steps out? No. Formula, numbers, answer. You don't have to go in that kind of detail. I'm just doing it to make it clear to you. This 5 is calculated. This means you could have made a mistake. When you want to use trig to calculate the angle, I would avoid using one of the calculated sides, because if you made a mistake with that number, you're going to have a mistaken angle as well. That means tangent is your best option. And you'll get a 53-degree angle, which makes sense because the triangle is a little higher than it is wide. What happens if you decided to use the 5 and you use cosine or sine and you were mistaken in this 5? I don't compound errors, meaning if you make a mistake once and you use that mistaken number in further calculations, I won't keep penalizing you for the error. As long as your steps are correct, I'm not going to go, oh, you used the wrong triangle side, that's -1. Now you use that wrong number in the next calculation, that's -2. No, it's the same error. You're just now carrying it through the equation, so I would only penalize you once. And there's your final answer in its glory. You put the vector together, you're good to go. Once. I only want to see this demonstrated once. You may have heard of these terms before. The plane has its airspeed, the wind speed, and there's the ground speed. What's the true velocity of the plane? Well, since we're on the ground looking at it, we see the ground speed. Now let's do a multi-part journey. These are the 4 steps you're going to take. You go 6 meters east, then 2 meters north, then 3 meters northeast, or 3 meters east 45 north, and finally 8 meters west 14 degrees north. If we look at these vector here, you can clearly see I've cheated. This is not 3 meters. Right? If this is 1 meter and 1 meter on a square, then doing this, I've cheated. It would actually only be to about here. I don't care. If I were to ask you to draw a diagonal on screen 3 meters northeast, I'm not going to go, well, you didn't calculate the trigonometric. No. This is about basic learning. I don't need you wasting your time doing that when we only have a week per unit. There's the displacement vector. The object started here, it wound up there. The path is irrelevant to the vector. The vector just says, where were you? Where are you now? How do we calculate our total displacement and our total distance? Distance is easy. Add them up. You're done. Displacement, slightly trickier. Let's zoom in on it. It's a simple triangle with base 1 and height 7. This means we're going to be very close to 7 on this. It has to be larger than 7, so it's going to be like 7.1. Maybe we could go as far as 8. And what does this look like to you? Like 80 degrees north? So you should be okay with this, providing it's a scale diagram, which is not a safe bet with the textbooks. This would be fine by me. Notice I used the absolute value signs here. You don't have to. They tend to cause confusion until you're about first year university and you get used to them. You could just write D without the vector. I know what you mean. You've done enough to establish you know what you were doing. That will be fine. And to get the direction, look at that. You guess about 80 degrees, comes in about 82. Put it together as a vector, number, units, bearing. And you're done. What would be the speed and velocity now under this circumstance? Well, we knew the distance was 16 meters. Look what I've done. No, I must fix that. 16 meters over 4 seconds is 4 meters per second. Remember, that's 6, 8, 16, no, 19. 19. Okay. There's my error. Oh, that's even harder to fix. Dang. That's going to take me half an hour to change that graphic. And the velocity was 7 meters over 4 seconds. Hello! There we go. 7 meters over 4 seconds. And we get that. Notice how I did my meters per second. I'd avoid the slash s. It much nicer to do it this way, and you'll see why. I know it's nice to write m/s, but it's going to create confusion later on. So there we go. Now, which of these really represents the actual speed of the object? This object, was it moving at 4 meters a second? Or was it moving at 1.75 meters a second? Which one is a mathematical illusion, I suppose? Or what would happen is if you did it in a single pass? And which one represents really what you would be hit by if you got in its way? This is what textbooks can do to your brain. And this is what I meant, you have to pay attention. If I gave you these two values, 100 meters east, 5 meters north, and you were to calculate the displacement vector, both its magnitude and direction. So we have 100 and 5 meters. You're going to hit, deliberately in this case, what's called cognitive dissonance, where two things don't agree. Can you take a look at what I've done that would deliberately confuse you on this page? And the textbooks do it all the time. There's something here that you would carry out these calculations and then look at this page again and go, I screwed up. That can't possibly be right. It'll make you feel stupid, and you're actually not. It's laziness on the part of the people who wrote the textbook. And in my case, I've done it on purpose because this used to happen to me all the time.